Let's work another rotational kinetic energy problem. So in this one, we're going to make things a little bit more complicated. We're going to have a solid disk that has a mass of 2 kilograms and a radius of 0.2 meters. And we're going to put a hanging mass over here that has a mass of, say, 4 kilograms. And then we're going to put another one down here that has a mass of, say, 3 kilograms. And we have this thing a distance 1 meter off the ground. And we're going to release this mass and let it fall. And what I want to know is, what's the velocity of this thing right when it smashes into the ground? So what's the velocity here if it started at rest here? Now, we could use Newton's laws of motion to solve this problem. We would have to find the net force acting on each block. We would have to find the net torque on the wheel. We would have to do about 3 equations, substitute things in there to get the acceleration, then use kinematics to get the final velocity. Or we can use conservation of energy, which streamlines this problem a little bit. So, in this position here, this wheel has no energy because it's not moving and it's fixed to the ceiling. It's not going to fall. So it has no energy as far as we're concerned. This 4 kilogram mass has some potential energy because it's got some height. This 3 kilogram mass doesn't because its height is 0. So at the beginning, all we have is potential energy, and that potential energy is equal to mgh, which in this case is 4 times 9.8 times 1. That's our potential energy that we start with. Now, as this thing falls, so this is our total initial energy at the beginning, then this changes because the 4 kilogram mass loses potential energy, gains kinetic energy. The 3 kilogram mass will also gain kinetic energy, but it will also gain potential energy because it's getting higher. And this wheel is going to gain some rotational kinetic energy as it spins. So at the end, our total energy is given by 1/2, this is kinetic energy of this thing, 4 times its velocity squared, plus 1/2, 3 times the velocity squared. Now technically these two things have, well, if you choose positive is this way, then they have the same velocity. If you choose positive is up, then they have opposite velocities, but we're squaring it, so the sign doesn't really matter. 1/2 mv squared plus 1/2 mv squared of this thing, plus it will also raise to a height of 1 meter. So plus 3 times 9.8 times 1, because it's gaining potential energy as it gets higher, plus this thing will gain kinetic energy equal to 1/2 I omega squared. Okay? All of this right here, the energy at the end, has to equal that, the energy at the beginning. So this is equal to 4 times 9.8 times 1. Okay? Now let's see if we can simplify some of this mess and get rid of some stuff. Because I have an I and I've got an omega and I don't want to deal with that because all I want is V. So 1/2 of 4 is 2, so I have 2v squared plus 3/2 v squared plus 3 times 9.8 is 29.4 plus 1/2 I omega squared. So I, for a solid disk, is 1/2 mr squared. And remember, v equals omega r, so v squared over r squared equals omega squared. And so if I make that substitution, I can say v squared over r squared equals 39.2. Now we can collect like terms and get rid of some stuff. Oh, and I know the mass of that wheel. The mass of that wheel is 2, so I'm going to put that 2 in there. So 2v squared plus 3/2 v squared. I can subtract this 29.4 over, and that's going to get me 9.8. Plus 1/2 of 2, the r squareds cancel, 1/2 of 2 is 1, so plus 1/2 v squared equals my 9.8. So I have 1/2 plus 3/2, which is 2, so I have 4 v squared equals 9.8, and I can divide both sides by 4, get v squared equals 9.8 over 4, and then square root that and get v is equal to the square root of 9.8 over 4. I don't know what that is. That's how fast this thing is going when it smashes into the ground. We were able to use conservation of energy to do that problem. And it solves fairly straightforward. We don't have to know the tension in this rope. We don't have to know the tension in that rope. All we care about is the energy at the beginning, the energy at the end.